So today's last speaker is Dmitrii Rachenkov. So his title is Quadratic Differentials and Degenerate Eigenvalues.
Okay.
So
Thanks a lot. So I want to thank the organizers for the possibility to talk. It's a pleasure. Can the mic work?
Yes.
Okay. Thank you. Okay, today I'm going to speak about quadratic differentials and degenerate eigenvalues. First of all, here are some references where you can go to see the whole story. I think I will sacrifice the scientific part to be more introductory, but maybe I will have still some time to do it. The last work by Bertol, Grava, and Chavez Heredia was about, it was connected to Penlever 2, and my project has a connection with the Penlever 4 equation. And yeah, this is what I'm doing. But I'm going to present only a part of the work about Stokes data. And if I leave you with a feeling that Stokes data has a natural cluster structure, I will be happy. What we want to do, we want to consider maximal in details the equation, the simplest one. Can you see? Okay, nice, thank you. The simplest enharmonic oscillator, maybe the simplest one is with xy, but it's not interesting for our purpose. And I want to do everything for this equation. First of all, we want to understand something about solutions of it, because it's enharmonic, and we can't solve it for generic parameters precise. So we want to apply WKB analysis. Small reminder. What we do in exact WKB analysis, normally we have an equation like this with a small parameter and the potential. That also depends on this small parameter, but it is just a polynomial in it. So V in my case equal to V0 plus H V1 plus H K Vk. All of them depends on X. And in this case, we can try to search for a solution in the view of formal power series. Where S is a power series that starts with the first negative degree on small parameter. And goes to infinity. If we plug this solution into this equation, we will get a Riccati equation of the next form. And from this equation, we can conclude that this power series satisfies some recurrence relation, which can be solved step by step because there is a filtration in the small parameter h bar. And the first equation for S minus 1, can you see it's maybe small, I don't know. S minus 1 square should be equal to V0. It's for I equal to minus 1, and for I bigger minus 1, there are some other recurrence equations that can also be solved. But what we can see, this equation gives us two solutions that we will call plus and minus. And morally, these equations, the solution will look like integral 1 over h bar plus minus square root of V0. Maybe to be more precise, this power series is like strongly divergent. We need to do something, and one of the methods is to take a Borel summation. I don't want to define it. But we can use the final result. So we can say that the first term of the principal term of this expansion of the divergent power series here might be written as this is a formula, and okay, it's also multiplied by the higher terms in H bar. And when we do a Borel summation, we will get the same kind of asymptotics. And the moral of this story, for the convergent, we care about this term and about the imaginary or real part of this under integral equation.
Where does it stop? E to the power something.
Can you put a parentheses around?
Yeah, sure. Sure. It was like this.
Thank you.
And here it was like this.
No.
So sorry for writing like this. And the Borel resummation not always work. It doesn't work always. So to be Borel summable, for this equation, it will mean that imaginary part of the integral will equal to 0, where tau is a 0 of our V0. So that's kind of turning point. Coming back to our equation, we can introduce by hands H bar parameter, but it's not so necessary. And I want to write the picture, I want to draw a picture for these points that satisfies this equation. Let's draw it big. We have only one parameter C. This is a real part and this is imaginary part. If I take a point on the real line for parameter C, and then I want to draw a picture for the x-plane that will be associated to this point. We have two zeros for the equation. That belongs to the real line. It's a minus square root of C and plus square root of C. And they are our turning points. Next to the turning point, if the zeros are simple, this equation just proportional to square root of z. And after the integration, it will be z in 3/2. So it particularly means that from each point, there will be 3 rays going outside, 3 lines. And from the symmetry, we can conclude that the picture will look like this. These directions actually corresponds to the Stokes or anti-Stokes lines, depends how you call it. If you pick up a point on the negative real line, the picture will be like this. Where it's square root of c minus square root of c. Interesting thing happens when you pick up c from with a positive imaginary part or negative imaginary part. In this case, the picture will look like this. And in opposite way, it will look like this. What I'm trying to say is that there is some phenomenon of wall crossing that happens when we cross the line of the real line of parameter c, because it changes the behavior of our Stokes lines, Stokes diagram. Here, at the same time, we can see some triangulation. Let's use a different color. We can connect infinities in our picture, in our x-plane, like the boundary and the complement line between our natural triangles that comes from our Stokes lines. And this transformation corresponds to the flip in our triangle. Moreover, we can see, we already saw that the behavior of the topology of the Stokes graph depends on the first term, and we can do the next transformation. It's called the Seibert curve or spectral curve. We write down our initial equation in the matrix form. Next way. As a linear differential equation, where in our case it is just a y dot it is the same equation. And the transform, the spectral curve that I want to consider defines as a determinant of the difference between lambda identity and A. And it is, in our case, equal to lambda square equal to V, but we will be interested only in V0. It's a double cover of this space. Maybe I can use this. Oh, let's draw again. This is the picture. It's a double cover. So to consider it, I want to associate some branch cuts at every point, every branching point. And here I can also look at some special class of monodromy loops. I want to look at, for example, that kind of loop, gamma. And the cluster coordinate that we saw before will be defined as x gamma h equal to similar 1 over h bar. We can put it in front. Square root of, I can put just lambda of z around the gamma. It's lambda z, it's the same as square root of vz. We just need to integrate by around like both sheets. And you can see already that this formula, if you, it is similar to the tropical formula. When you do a limit by h bar, it will give us the same formulas that we saw. Where is the cluster structure? For this purpose, I will draw a more complicated picture. Well, for cluster structure, you want to have a Poisson bracket, a quiver. So let's do it. This is my triangulation. Here you can think that I'm drawing a picture for the cubic potential. So V is equal to V0 x cubed plus Ix plus B. Here are my branch cuts. And let's do 2 loops. Okay. So gamma 1 and gamma 2. These 2 loops intersect only in one point. The second point, it belongs to different sheets. And the form of intersection, it's just an intersection form in first homologies in a spectral curve defined by this equation in this double cover. And it will be it will coincide with the classical rule that how we do a quiver from a triangulation of n-gon. We say that we associate a vertex to every internal edge, frozen vertices to boundary, and the arrow that goes counterclockwise in every triangle. Frozen vertices are not important for dynamics, for description of our cluster algebra, because we will never mutate in them. And here are our main part, exactly that corresponds to these 2 cycles, and this is one intersection. To check the time, okay. So far, I tried to convince you that our Poisson structure, so our Stokes data naturally has a Poisson structure. Why? Here you see that our monodromy data has a Poisson structure. But at this point, we did some sort of abelianization of our problem. We want to replace this equation of size 2, or like in general, this work is not, I think, done in general, but for n rows, you can try to do the same thing. Sorry, here we miss a differential. We can try to do the same thing, the same determinant, the same cover, and try to solve only linear differential equation, like only differential equation, scalar. What the word? So we reduce the complicated Stokes data, some matrices, just to monodromy coefficients. And that's it. Okay, I think I have some very short time to say about the research, about eigenvalues, what you want to do. We consider similar equation just for x in degree 4, and with a pole. Oh, sorry, x in degree 2, but with a pole at 0. It means I have 1 minute. And we apply Frobenius method. We just plug power series inside this equation, and it solves a lot, because the whole equation just becomes like a k diagonal matrix. With infinities in one side. And then we ask to have special solutions that look like a polynomial multiplied by exponent. This part we could see already for this equation, because for some special C, I think which is, I don't remember the formula, but the solutions of this equation, one of it, will be a Hermite polynomial with an exponential prefactor like this. But we go forward, we ask about adjoint solutions of this equation. And we ask also a joint solution to be of this form. And it has some connection to differential Gola theory that I will not definitely present now. But the pictures of polynomials will coincide, will be very similar, not coincide, but this is a conjecture to explain, with the rational, with the polynomials that comes from the rational solutions of Mendeleev equations. I'm done. Thank you.
Is there any question or comments? Please.
Here, in your example, you obtained the cluster algebra of type A2, right?
Yeah, this is A2,
yeah.
and this is A1, actually.
So in your other examples, you will also get this finite type?
This is A3, and this is cluster algebra of this type, which is not finite.
Okay.
Because we have one singularity inside. There is a diamond model.
So you can get infinite types. Yeah. Thank you.
Can I ask you, so this VO, this potential is the coefficients of Y in that case? I mean, first you introduce X squared minus C.
Yeah.
Is it related to A1 case?
So this is A1 case.
A1 case.
Sorry. This was example, the whole example only for that equation.
I see. Then if you replace X squared minus C with this BO, then you get A2.
Sorry. This is
Okay.
In most cases we have V equal to V0.
I see.
So for some more complicated cases, it makes sense to have more terms, but so first step.
But does the story go on? Like if V0 has higher and higher degree?
Sure, it's not a problem. It's done by Dillon Allegretti for polynomial potentials.
Right. And the end is what? Which cluster algebra?
Sorry, Vn, you mean like a polynomial of degree?
Higher degree.
So when V0 equal to x n...
X to n plus 1.
This x squared correspond to A1 and x cube correspond to A3 and so on. I'm bad with adding +1 or +2. You can see. Sorry. And the last maybe comment, this is, I don't want to hide that this is a stability space for A1 quiver, factorized by this functor.
So this reminds me of potentials in Arnold's singularity theory. Are there cases with two variables that would correspond to other types of cluster algebra?
You mean with two variables, you want to have a connection, or?
No, I meant a polynomial potential, but usually the type D singularity has another variable. Type A has only one variable, right? Type D has two, etc.
For D type, I guess it's a triangulation of one punctured polygon.
Right.
So maybe there is something, but
Yes.
for E-type, such an interpretation doesn't exist in terms of triangulation,
I don't know.
as far as I know.
Yeah, I think triangulation is like necessary, but you also think about the triangulation on the sphere. We must think about triangulations on any Riemann surface. So here it is still genus 1, but for the polynomial of degree 4, it will be a genus, genus 0 and genus 1 and higher. Yeah.
Questions? Okay, let's thank speaker again.
Thank you.